So the key idea, two key ideas last day, right-hand rule number 3, and we said this. If a charged particle enters a magnetic field, as it gets deflected, it's going to eventually get bent into a circle, which meant we asked, what path is this particle tracing out? And you all said, a circle. I said, which way is the net force? And you all said, towards the center. And I said, that means just like in orbit, when we said gravity equals circular force, we can say magnetic force equals circular force. We can say QVB equals mv squared over r. QVB equals mv squared over r. Oh, and then in a wonderful coincidence, one of the v's canceled, and we had 1, 2, 3, 4, 5 variables. And I said to you, I can give you any 4. We can find the 5th. Oh, as long as, Taylor, the magnetic field and the motion of the charge are at right angles to each other. We said if they're parallel, it's really the charge experiences a force when it crosses magnetic field lines. So let's try an example. Example 2. An electron, let's all underline the word electron, moving at 3.2 times 10 to the 6 meters per second, enters a perpendicular 0.545 Tesla magnetic field and traces out a circular path. What's the radius of this path? John, what are they asking me to find here? I think this sounds like, a charge being forced into a circle. Magnetic force is pushing it into a circle. I'm going to drop the vector since I don't actually have a picture here. I'm not going to be able to get a direction, and besides, radius doesn't have a direction. It's, towards the center. What's the force on a moving charge? QVB. What's circular force? Don't write this down. It's mass times circular acceleration, but we never actually wrote MAC. We jumped straight to plugging in an equation for circular acceleration. There was 2. There was the 4 pi squared r over t squared. We won't be using that this unit. It's almost always going to be v squared over r. But you will have to remember where that is on your formula sheet again if you don't have that still in your brain. Conveniently, one of the v's cancels. Now, by the way, I like this question, I like this question, I like this question, this will be a written question. And this is a written question that drives me crazy. Because every year, and I don't know why, every year I see kids do this, and then they go, R equals QB over MV. Is that right? Is that correct, Ben? No. I don't, suddenly, because I thought this was like a Physics 11 rewrite. Hey, that's going to move to up. Those are going to move down. Every year, I don't know why, I haven't figured it out. It's only this equation that they do it on. They're able to cross multiply just fine on FC equals FG, MV squared over R equals big G, big M, little M over R. They get that one just fine. But kids botch cross multiplying this. So I've done my rant, hoping to prevent it. It's going to be MV over QB. Oh, by the way, since we're towards the end of the year, I've seen this before, and I think you might in the future as well. What is mass times velocity? We've given that a name. It's momentum. Actually, I've seen it, instead of giving you the mass and velocity, they just told you the momentum of the mystery particle. Oh, cool. Or you could actually find a particle's momentum by, I guess, Q times B times R is the momentum of the particle. Even if I don't know its mass or its velocity, I can tell you its momentum. So there's all sorts of stuff hidden in here. For now, though, mass. It's an electron. Chelsea, what's the mass? You got your yellow sheet. What's the mass of an electron? I know it's 9.11. That one I remember.
Yeah, 10 to the -3.
Velocity, they gave me 3.2 times 10 to the 6th. All over. Q, it's an electron. B, that's magnetic field, 0.545. What would the radius of this path be? which means if I was doing this particular experiment and I had a photographic plate and I saw a particle with this radius, I could be reasonably confident that what I was seeing was an electron. Although it could be 2 electrons, because if you double the mass and double the charge, the 2's cancel. But anyway, there's a little more to it than this. Let's see. 9.11 times 10 to the negative 31 times 3.2 times 10 to the 6th divided by bracket 1.6 times 10 to the negative 19 times 0.545. Did I type this in right? Do you get 3.34 times 10 to the negative 5?
Yeah.
Woohoo! Small radius because I made up these numbers and these are bad numbers. I really should have had this particle traveling at 10 to the 7th, but that's okay. 3.34 times 10 to the negative 5 meters. Hey, which provincial exam is example 3 from? January 1990. That's just after I graduated. As shown in the above diagram, a proton, let's remember that, entered a magnetic field at location A. By the way, let's use our right-hand rule for what it's worth. Which way is the proton traveling right here? Up. All of you point your thumbs. Let's use this as our paper. This is for Gabby. All of you point your right thumbs up. Which way is the magnetic field? What do those X's mean? Into the page. Extend your hand. Gabby, you want to play along with me? Into the page. Which way is your palm pointing? To the left. It's going to get deflected that way, that way, that way, that way. That's what's deflecting it in a circle. Okay? So the diagram is right, but it was a good chance to review our right-hand rule. They gave me the radius. They gave me the magnetic. Oh, what are they asking me to find in this question? Speed. Or technically speed because they're not asking for a direction, but yeah, we've called it velocity all year long. We've been sloppy. Is it moving in a circle? Is there a magnetic field? Is there a force? Why, I think what we're really saying is the magnetic force equals the circular force. QVB equals mv squared over r. Hey, one of the r's so one of the v's cancels. What are they asking me to speed? Okay, get the v by itself. Equals what? Get the v by itself. QBR over m. Have I got room? Oh, lots of room. V equals Q. It's a proton. 1.6 times 10 to the negative 19. B, they told me, 0.02. It's 2 times 10 to the negative 2, but it's less typing on my calculator to just get rid of the scientific notation. R, 3.25. Big radius. All divided by m, mass. It's a proton. This one I don't have memorized. It's 1.67, but I don't remember the exponent.
27.
Negative 27? So, if I knew I was dealing with protons, if I had some kind of a proton source, and I knew the strength of my magnetic field, and I'll show you in a second how we can create magnetic fields of any strength that we want, why then I could calculate its speed. And since usually these speeds are pretty high, there's got to be some way that you can calculate it, because strictly measuring it, pretty tough with a stopwatch at this speed. What do you get, Ty? What point what?
6.23 times 10 to the 7.
Anybody else? Is Ty the only one that did it? Josh, you got it too? Yeah, you did? Same number? because I mean it's tie, right? 10 to the 6th or 10 to the 7th?
10 to the 7th.
All right, Mr. Dewick, you tried to get away without typing this. Okay. 1.6 negative 19 times 0.02, because that is 2 times 10 to the negative 2, times 3.25 divided by 1.67. 1, 2, 3, 4, 5, 6. I knew my doubt was correct. Never trust him. Okay? So, I guarantee one of the written questions on your test is going to be giving you a situation where a charge is being deflected in a circle, and I'll ask you to find one of those 5 things, and I'll give you the other 4, or I'll give you enough information to find the other 4. So that's on an individual charge, but you may recall last day I showed you a video of not just a charge moving, but of a whole wire jumping. What would the force be on a current carrying wire? Well, what you can think about in a current carrying wire is that it's a whole bunch of charges all holding hands. So really what we need to do is just figure out the force on one charge and, well, I'll show you. So if we have a wire carrying a current perpendicular to the external magnetic field, it will experience a force, and it can be calculated by using what we call the right-hand motor rule, the point, high-fi, palm. It turns out it depends on 3 things. Well, watch. Right now we have this. Yes? Don't write this down, just watch. Another way to write velocity is distance over time, because it's meters per second. If there's no acceleration, let's pretend there isn't. Is that okay so far? Except instead of putting the t underneath the d, I'm going to put the t underneath the q. Now, why am I doing that? What is charge divided by time? According to your formula sheet from last unit. Huh? Current. Ah, this is, which comes in handy because now we're talking about wires. Instead of D, we're going to call it L for the length of the wire. Magnetic field. As an equation, the force on a wire is Bill. Come on. Is B-I-L. If the, just, come on, pen. Scroll up a little bit. Let's try it again. Force on a wire is B times I times L, as long as all of these are perpendicular to each other. Okay. And that really is your force on an individual charge in disguise, just saying, well, if I got a bunch of charges, how many? Well, I guess that's kind of the length in the current. So example 4 says, find the magnetic force and the direction on a wire. Okay. Magnitude. B-I-L. Double check. Is the current, the length, and the magnetic field all at 90-degree angles to each other? Specifically, is the current and the magnetic field at 90-degree angles to each other? Yeah? So really the length doesn't need to be perpendicular because the current and the length are parallel. Magnetic field, 6, huge. We saw the video last day of the, 4.5 Tesla MRI machine destroying things. Current, 5. Length, not 70, 0.7. I think I do this in my head, no calculator required, Tyler, because I think 6 times 5 is 30. And I think 30 times 0.7 is going to be 21 newtons. Now that's the magnitude. Direction. All of you try using your right-hand rule on your own. Ready, Gabby? Here's how it works, kiddo. Lift your paper up so it's vertical, just like my screen. You point your right thumb in the direction of the current. your fingers extend like you're going to high-five in the direction of the magnetic field, which means I got to bend like this. Yes? Which way is your palm pointing? That's the direction of the force. My palm is pointing which way, folks? Into the page. If you're still having trouble with the right-hand rule stuff, same as I said to Gabby earlier, I'm going to be flogging it for about 3 days. Your test, I think I mentioned, I'm aiming towards Wednesday the 15th as your unit test. If you get to the end of next week, so if next week on Wednesday you're still shaky on the right-hand rule stuff, then come in and I'll walk you through a bunch of examples. But for most people, it's suddenly, aha, will click over the next couple of days as you look at applications. Example 5. If the force on a 5-centimeter piece of wire carrying 12 amps is 1.0 times 10 to the negative 3 newtons, what's the magnetic field strength? Is there a wire? Is it perpendicular? Is there a magnetic field? Why, Jaron, I think there is a force, and the force on a wire is Bill. Ben, what are they asking me to find in this question? What's that in my equation here? B. Ben, my friend, what does B equal? Oh, this is kind of straight plug and chug. 1 times 10 to the negative 3 divided by I, 12. L, oh, careful, it's not 5. 0.05, they gave it to me in centimeters. .001, that's what 1 times 10 to negative 3 is, divided by 12 times 0.05. This should work out like almost, yeah, there you go. 1.66 times 10 to the negative what, Tyler? There you go. 1.67 times 10 to the negative 3 units. It's magnetic field. Teslas. Our new unit for this unit. Turn the page. Applications. This was a little better 10 years ago when the movie was a bit more current, but I have to ask, because it's a pretty good movie, and some of you may have seen it. Anybody see the movie called The Hunt for Red October? The Hunt for Red October. It's a classic Tom Clancy, Sean Connery. The premise is that it's a movie about the Cold War between the U.S. and Russia, specifically looking at submarine warfare, because both the U.S. and Russia realized that the best way to have a nuclear threat was to have some hidden, unknown nuclear weapons underwater somewhere. Who knows where? Could they be off the coast of New York? We don't know. And so in the premise of the novel and the book and the movie, the novel and the book, the novel and the movie, the Russians have invented a no moving parts, water running jet engine for their submarine, which means their submarine now is basically undetectable by the U.S. And here's how it works. This is in theory. I don't know if it's been built yet, but this is the theory. Here's how you could build a jet engine underwater with no moving parts. What you do then is you have a North Pole magnet and a South Pole magnet. So the magnetic field is like that. Can you point your thumbs that way, please? Can you please draw the magnetic field that way? And although you can't see it, Terry, what we've done is we also have a a metal plate right here, about the size of my hand. So imagine that it's like shaped like a box, but you can't see this. And in this metal plate, we run a current. Now, seawater is conductive, so once we send a current into this metal plate, it's going to run into the page. That's what those X's are. So you ready? Point your right thumb in the direction of the current, which for me is into the page. Boom. Okay? Which way is the magnetic field? Down. Which way will the charged water particles feel a force? out the back like a jet engine. This will cause charged water particles to go scooching out the back, and Newton's third law then says, oh, you'll also have a force pushing the sub forwards. Not on your test, you don't need to know that, but it's a cool application. For what it's worth. So if you're one of those people who's like, is it on test or not? You can put a line through this question. I just couldn't resist the application. Solenoids. I said a few minutes ago, hey, it's possible for us to create any size magnetic field that we want. It is. Using a solenoid. What was a solenoid? We said if you took wires and you wrapped them together in a circle around some kind of an object, that formed an even stronger magnetic field called a solenoid. And it turns out in a solenoid, what's going on, what variables you have are several. First of all, the variables, N is the number of turns. Twice as many turns, you're going to get twice as strong a magnetic field. Yeah.
So if you use really, really thin wire, but you wrap it around more times, it'll be more.
Yes. Except the thin wire can't handle as big a current without overheating. And you'll notice another variable is the current. Okay? And another variable is the length of the solenoid. The closer they are together, the wires, the closer you wrap them together, the more they overlap, the closer they are, the stronger the magnetic field as well. In fact, Ampere determined the magnetic field inside a solenoid. By the way, let's double check our solenoid rule. Which way is the current flowing in those wires? Imagine you're holding the solenoid in your hand. I think the current, Chelsea, is coming over this way. Is that the North Pole? Yeah, the magnetic field lines, that's north. On the outside, right here, it points from north to south. It points left. Inside, because magnetic field lines never end, inside the magnetic field pointing to the right, but outside the magnetic field will be pointing to the left. Ampere determined that the magnetic field inside a solenoid depends on three variables: current, number of turns of wire, and the length of the solenoid. In other words, turn the page. He found that magnetic field was proportional. He found that magnetic field was proportional to the number of turns, the size of the current, but inversely proportional to the length of the wire. He said shorter is better, longer is worse. But he needed now a constant to get an answer in Teslas. The same way as we brought big G, 6.67 times 10 to the 11, to get an answer in newtons. The same way as we brought K, 9 times 10 to the 9, to get an answer also in newtons. We need a constant to get an answer in Teslas. And the constant that you need is called mu naught. So here's the equation. Magnetic field of a solenoid is mu naught, or mu zero, but I had a British physics teacher, so I'll always call that mu naught. N I over L. Where mu naught is on your formula sheet, on that front page where all the constants are, go find it. What is it, Gabby?
4 pi times 10 to the negative 7.
4 pi times 10 to the negative 7. And then the units are what you need it to be in order to get Teslas on the left-hand side of my equation here, because you need it to cancel out current and cancel out meters on the bottom. Anyways, 4 pi times 10 to the negative 7. First of all, this is one of my favorite constants because it's got one of the best names. It's called the permeability of free space. If that's not a great name for a constant, what do we call big G, the gravitational constant? Meh. What do we call mu naught? The permeability of free space. Chelsea, what did you learn in school today? Mummy, I learned about the permeability of free space. I mean, I love that name. Also, the nerd in me loves the fact that, holy smokes, pi rears its ugly head again for some, or its lovely head again. Pi shows up. What the heck does pi have to do with the permeability of free space and magnetic fields? The universe seems to like the number pi because it shows up in some bizarre places. By the way, it shows up in some really bizarre places. If I try and do a graph of all of the students in BC's provincial exam scores, and I want to use the normal standard distribution, the bell-shaped curve, that equation has a pi in it. And what the heck pi has to do with how an average student will score on a test should scare you. Anyways, magnetic field of a solenoid. So mu naught Ni over L. Actually, there's a second version of this equation. Sometimes instead of telling you the total number of coils and the current and the length specifically, sometimes instead of telling you the number of coils and the length, they'll just give it to you as a ratio. They'll tell you how many coils per meter. Instead of saying 100 coils and 1.2 meters long, they will just say, oh, it's this many coils per meter. So you'll also see on your formula sheet that this equation can be written as, come on, pen. Come on, pen, don't kick out on me now. You've been doing so good. Okay, let's see if I can do my repair. I've been doing so good. Okay, pen is back. There's a second version on your formula sheet. You'll also see that B equals mu naught little n times I, where n equals the number of turns per meter. Number of turns per meter. I know we're supposed to spell meter with an R-E in Canada, but that always just looks weird to me, so I'm going to spell it like that. Anyways, turn the page as an example. A solenoid is carrying a current of 4.2 amps. If the solenoid is 1.2 centimeters long and is made up of 750 turns of wire, what's the magnetic field at its center? Magnetic field of a solenoid is mu naught big N big I over L. And all of you want to try this on your calculator because typing in 4 and then pi and scientific notation on some of your calculators might give you an error, in which case I'll have to show you the workaround. So all of you want to try this. It's 4 pi times 10 to the negative 7. N is the number of turns of wire. Megan, how many turns of wire does this solenoid have? I is the current. Dorothy, what's the current of the solenoid? Yep. And the length, careful, it's not 1.2 Diana. What is it really? How about 0.012? Yes? I think you thought it right and said it wrong. I do that all the time too. All of you try typing this in because that 4 pi on some of your, on the graphing calculators, it should be fine. On the scientific ones in particular, you may get an error. It worked for you, Ty? Oh. All of you type this in. You need to find out, your calculator might not let you type it in. My whole point. You got an error? Yes, that's what I'm trying to find out. I don't know, let's find out. 4 pi, scientific notation button, negative 7 times 750 times 4.2 divided by 0.012. Do you get 0.33 Teslas? Now, what's nice about this is, what if I wanted a slightly smaller magnetic field? Hey, unwind a few turns of wire. What if I wanted a slightly stronger magnetic field? Add a few more turns. What if I wanted exactly twice as strong? I got two options. I could double the number of coils or just double the current. It gives you complete control. You can create any size magnetic field that you want to fit your needs very easily. Change the current or change the number of coils. So you either manufacture a solenoid with a certain number of turns in the factory for a certain situation, or, we learned last unit in circuits, it's very easy to vary the current you want by just changing the circuit. Number 8. Here, we're looking down the end of the solenoid. Yep.
So it's like a MRI machine, just like a giant solenoid?
I believe so, yeah, and I need to double check that, but I'm pretty sure that's why you're inside a huge solenoid. That's why it's shaped tubularly, yes. And in fact, later on today, I'll show you a video of the world's strongest magnet, as far as I know, 45 Teslas. And it wrecks the cameras. They actually can't get any video of it because when they get in the same room, the cameras, since all technology now involves moving electrons and charges, they won't go where they're supposed to go because they're getting deflected by a magnetic field, things you don't think of back in the analog day. So here we have a solenoid. We're looking down the end of it. You can imagine if you want to, if I wanted to go with a 3D picture, something like that. But I just didn't want to muck around with it. It says find the field and the direction, let's underline and the direction, at the center of the coil. The coil is carrying 10 amps of current and has, here's the second equation, the second version of the equation. Instead of telling me the length and the number of coils, they just told me it's 2,550 coils per meter. And that's often what, if you buy a solenoid as an electric part, you'll find often that's what they're giving you on the side of the package, the number of coils per meter, not the length and not the number of coils. It's just a ratio. So, magnetic field is going to be mu naught little n times I. Can you tell how I figured that out? That I knew to use this one, by the way? They didn't give me the length. They didn't give me the number of coils. They gave me coils per meter. I'll give you one of each on your test, I'm sure. It's going to be 4 pi times 10 to the negative 7. 2,550. 10. Get the magnitude and then we'll get the direction. Four pi times 10 to the negative 7 times 2550. By the way, who has scientific calculators? Who has scientific calculators that have built-in constants? Some of you do. You might want to double check. If you see in small writing a little mu naught somewhere, or if you look on your cover case, it may have a list on the inside cover of constants that are built in. A lot of calculators have big G built in, little k built in, and mu naught built in which case it's less typing if you know how to use it. Not all, but some do. Do you all get a magnetic field of 0.032 Teslas? Now, that's the magnitude. What's the direction inside the solenoid? We have to imagine curling our fingers in the direction of the, we're holding the solenoid, we're using a right-hand solenoid rule. If I were to hold this solenoid, I think my fingers would curl in that direction, yes? So is north coming, which way is north in the center? What do we call that direction right there? Out of the page. How could I show that? What was our symbol for out of the page? Okay, you know what? I'm going to go yoink, 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 and I'll even write here out of page. Right? Our symbol for out of the page was the tip of an arrow coming towards us. Now, this goes back to, Nico, your earlier question where you said, does that mean thinner wires will make a stronger? Technically, except thinner wires can't handle as much current because on a fundamental level with current, what you're trying to do is force a bunch of force a bunch of positive charges mathematically if they could move that way, but really it's electrons moving through a small area. Thinner wire means you're going to overheat if you try pushing more of them through because they're going to bump into each other and you'll get electric friction. Okay? But, hey, you got other options. A solenoid is to be wound on a cardboard form 30 centimeters long. How many turns of wire are needed if I want to produce a magnetic field of exactly 6.28 times 10 to the negative 3 Teslas if I know that the maximum current that this wire can handle is 5 amps? Okay, this is a solenoid magnetic field question. First thing I would do is I would write B equals mu naught, not little n, Mr. Dewick. They told me everything. Big N, big I over L. Do you have constants built on in yours, Ty? Because yours might be one of them. No? Okay. You guys really need to read your calculator manuals. There's all sorts of neat bells and whistles that you got. Jake, what's this question asking me to find?
L. No.
Good guess.
N.
Yes? Okay, Jake, my friend, recover, redeem yourself, get big N by itself.
N equals mu I L over F. Mu.
Leave this where it is.
Yeah.
Yes? How would you move those two over?
So,
Divide. How would you move this guy over?
multiply.
Okay, can I erase the arrows?
L over mu I.
I hope you went, it's going to be blah over moi. Yes? Whatever. Whatever dumb way you want to remember or keep these straight. Again, you know what? I'll give you a question. You notice there is 1, 2, 3, 4 variables and a constant. Hey, I'll give you any 3. Find the 4th variable. As far as I'm concerned, Alicia, it's fair game. And later on, I'm not sure which day, but one of these days, you'll be building your own solenoids. It'll be our final little lab activity after the field trip. 6.28 times 10 to the negative 3. L, 0.3, because it says 30 centimeters. I'm not falling for that. Nice try. By the way, you'll find in a lot of these they give you the distance in centimeters because solenoids generally aren't huge, aside from the MRI machines. Divided by, 4 pi times 10 to the negative 7. The permeability of free space. I just love that name. Current, 5 amps. So if I want to build, if I'm in a factory and I want to build this solenoid, and those are the criteria, how many turns of wire do I want to put around my solenoid? Now, I don't think this will work out evenly, so we'll have to round off to the nearest turn, I think. But 6.28. Although 6.28 is a multiple of pi, it might almost work out evenly. Oh yeah. I was trying to make it work out as even as I could. 300? Yes? 300 Teslas. No, I'm not finding B, Mr. Dewick. And number of turns of wire. Sheesh, what did I write B equals? Ty, haven't you learned by now not to write things down? As he gave me this stink eye. Oh, another mistake from Mr. Dewick. Hey, I think there's only 13 more classes left, so enjoy them while they're here. Hey, what would the units for this be? 300 what? Turns, sure. It's technically unitless. It doesn't have a unit in the actual equation. It's not part of the Teslas, but yeah, turns. Okay. What's your homework? Number 1, some right-hand rule practice as well. Number 2, now, take a look at number 2. Number 2, we have a floating wire. What are the forces acting on the wire? Get the obvious ones. Is it falling down? Apparently not. Oh, there must be a force pushing it up. They called it FM for magnet. I've been using FB for magnetic because to me, anytime I see an M, I think mass. Anyways, I think here your equation is going to be, but you're not going to use the big G, big M, little m. You're on the Earth. You can just use mg, right? And solve for whatever they want. Number 3. Okay. Number 4. So number 4, we have a cord that's supporting a mass. What are the forces acting on number 4? Get the obvious ones. Okay. Gravity down. Tension up. Is there a wire and a magnet? Which way is the magnetic force on that wire? Point your right thumbs in the direction of the current. Extend your fingers in the direction of the magnetic field, which I think is coming out of the page towards me. Boom. Oh, what's the force on that wire? Up or down? Jason? Down. There's also, so I'll let you see if you can figure out what tension has to be. I think tension's going to be mg plus fb. Okay. 5 is good, 6 is good, 7 is good, 8 is good, 9 is good. think I'm assigning all of these. 10 is good, 11 is good. Okay? You're going to have lots of time. Yeah, all of them. Got some cool videos to show you.